Our next topic is parity bit generators bar checkers. Okay, this is a definition. The circuit that generates the parity bit in the transmitter is called the parity generator. The circuit that checks the parity in the receiver is called the parity checker. Okay, so parity bit generator and parity checker. Okay, and the theory behind this is when the binary data is sent, it is susceptible to noise, and when the binary data is transmitted, the ones can be converted into zeros and zeros can be converted into ones. Okay, so when it is susceptible to noise or any disturbance while transmission. Okay, in such cases what we do is, for example, 1001 sorry 101 101 01 1 2 3 4 5 6 7 8. Okay, what we do here is count the number of ones 1 2 3 4 5. Okay, in this 8 bit 5 are ones. Okay, in parity bit generator what we do is, when the data is to be sent, an additional bit, it can be a 0, can be a 1, but most probably we add ones. Okay, when this a parity bit is added at the beginning, this is the parity bit, this is the data bits. Okay, what we do here is, we have a parity bit, we have the data bits. So the theory behind this is, when we send data, say for example this is an 8 bit data, 1 2 3 4 5 6 7 8, count the number of ones 1 2 3 4 5. Okay, when we send the data in an even parity bit generator, the number of ones, including the number of ones in the data bits, include, and also the parity bit should be even for even parity, odd for odd parity. I hope it's clear. Let me discuss this once again. These are the data bits db 101 10101. We are going to set what kind of generator or what kind of parity bit is to be added. Okay, so this is an 8 bit, 1 2 3 4 5 6 7 8. 8 bits are there. Number of ones, it means 1 2 3 4 5. Okay, so its number of ones here is odd. Okay, so when we need to set an odd parity bit generator, it's not the short form, I am just writing in odd parity bit. Okay, I will remove it. Okay, so for example it's odd. Okay, when it's odd parity bit, what we do is, it's already odd number of ones in this particular set, right? There are 5 ones, so what we do is we add the parity bit as 0. 0 will be the parity bit here. In another case, 101 101 again, this is the data bits, and we are going to construct an even parity bit generator. Okay, here the number of ones 1 2 3 4 5. So what we need to do is, we should add, it's 5 already, so what we need to do is, we need to add an extra bit. We cannot delete from the existing data bits, we can add one parity bit, so that the number of ones including the parity bit will be even. So we should add a 1 here. Clear? So what is the actual procedure here means, when, for example, if this data is sent across the network, okay, when it is transmitted, that's a case of attaching this parity bit is the duty of the in the transmitter section, that is a parity generator. And what about the parity checker? When that particular set is received at the receiving end, what they do is, they check, that is, there should be a means of communication between the sender and the receiver, that the data sent is of even parity. So the receiving end, if it is even parity, the receiving end will check whether that particular set including the parity bit has an even number of ones. Okay, so the receiving end, for example, if this is sent across the network, at the receiving end what they do is they check the number of ones including the parity bit. 1 2 3 4 5 6, yeah, it's even, so it's even parity, so there is no error. That's if the data is sent, and for example, if this particular data has changed, or the data due to noise, this particular data has been changed from 1 to 0, and this is received at the receiving end, there was a communication that it's what we call it's an even parity bit concept. So the receiver checks how many number of ones are there including parity bit, 1 2 3 4 5, but it's even parity, right? So what they do is they understood that there is an error in that particular received bits, so they will inform the generator or the sender that a data, then what we call an error has been detected. Okay, so the thing we need to think is for if the even parity bit generation is taken into consideration, what we need to do is the number of bits including the parity bit should be even for even parity, odd for odd parity. Clear? Please go through. Okay. This is the design of an even parity bit generator for 4-bit input. Okay. So what we do here is 4-bit means we need to write 4 bits name, variable names, and also 00000 to 1111. Okay, that is 0 to 15. That is 16 inputs, and based on that we need to write the parity bits. Here we are going to construct generate an even parity bit. Okay, even parity bit generator. So 0000. We don't need not add zeros there. So what we do is parity here. So we go for 0 there. Next is 0001. Number of parity means number of bits is odd, so we put a 1 there. Yeah. Then 0010, that is number of ones in this case is 0010 is odd, so we should make this even by putting a 1 here. 0011 means it's already there are even number of bits, even number of ones, so 0. Here we put a 1, 0. Here 0110 means already in even number of bits, 0. 0111, that is odd, right? So we put a 1, 1, 0, 0, 1, 0. 1101 means odd number of ones, so we put a 1 here, 1 here, and a 0 here. Let me check. 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0. Okay. Next step is constructing Carnot map. Constructing Carnot map, 4 variable K map. Okay, A, B, C, D. Okay, then 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 40, 50. Okay. For 1 we put a 1 here. For 2 we put a 1. For 4 we put a 1 here. For 7 1 here. For 8 we have a 1. 1 0 1 1. 1 0 1 1 here. 1 1 0 1. 1 1 0 1 here. 1 1 1 0. 1 1 1 0 here. So grouping means no pairs or quads, all individual cases. Okay. Please go through these steps. Okay. Next is solving. We have f is equal to, this is a bar, b bar, c bar, d plus a bar, b bar, c, d bar plus, this is a bar, b, c bar, d bar plus a bar, b, c, d. Yeah. Next is a, b, c bar, d plus a, b, c, d bar plus a, b bar, c bar, d bar plus a, b bar, c, d. Okay. Next is taking common terms. We have a bar, b bar into c bar, d plus c, d bar plus a bar, b into c bar, d bar plus c, d plus ab into c bar, d plus c, d bar plus a, b bar into c bar, d bar plus c, d. Again, this is equal to a bar, b bar into c plus d, c XOR d plus into c XOR d the whole bar plus ab into c XOR d plus a, b bar into c XOR d the whole bar. Now taking these terms common. Okay. So d into ab plus a bar, b bar plus c XOR d the whole bar into a bar, b plus a, b bar. This is equal to XOR d into c XOR d into a XOR b the whole bar plus c XOR d the whole bar into a XOR b. Okay. This is similar to a, b bar plus a bar, b, right? This is a XOR b, as you all know. So what we do here is write this in such a form. A XOR B XOR C XOR D. Let me check. Yes. A XOR B XOR C XOR D. And what about the diagram? Sorry. A and B. Yeah, XOR operation. A XOR B is over. This plus C. I mean, this XOR C. Okay, this is A XOR B XOR C. Write B here. This is F. A XOR B XOR C XOR D. Okay, I would like to give an exercise, the design of odd parity bit generator. Okay, the steps you need to follow is go for the truth table construction. Okay, where there are 1 values in the output, plot it in the Carnot map. No, it will be on the in all these positions where, I mean, all these vacant spaces, right? You know, in the case of odd parity, it will be filled and these places will be vacant. I think you have an idea regarding that, and based on that derive, you will get an expression. The expression will be, we write this f dash A XOR B XOR C XOR D, the whole bar. Okay, the whole bar. And about the figure, this part will be the same, and there is a bar on top. So what we need to do is construct this figure as such, and here we need to give a NOT gate and mark this as f dash. That's it. Okay, here in this position 3 XOR gates and a NOT will be there, NOT, and this is the expression A XOR B XOR C XOR D, the whole bar.